Today our goal is to look into what are called parameterized curves. Now the idea of parameterized curves is to say, let's find a better way to describe some curves. See, we oftentimes think of, well, we have a curve where there's this input x and something's happening to the output, y. But not all curves can be described that way, so we introduce a new parameter. And oftentimes we'll use the symbol t and think of it as time. So where we keep track what's happening with time. Well, let's begin. So, like we said, some curves can be described as a function, y equals f of x, but some curves cannot. It's impossible. Look, this is a perfectly fine curve in the plane, but there's no way to write it y as a function of x, because there's something called the vertical line test. And you see, if you draw a vertical line, there are some places where we have two values that we hit. Well, that means you cannot write y as a single expression involving x. Now, in a similar way, it cannot be x the function of y, because we say, look, there's something called the horizontal line test. And if you hit multiple times, again, for any value of y, there's no unique part for x. Now, there's a couple of different solutions to this. One solution, which is sort of our old mindset, would be, well, let's just break things into parts, and we'll deal with each part. And that works well enough when you can. In other words, we'd say, well, maybe we'll split into two halves. This first half here, and the second half here. For example, when we do circles, sometimes we do this, where we say y equals the square root of 1 minus x squared is the top, y equals minus the square root of 1 minus x squared is the bottom. But sometimes it's not so easy to do it. So how are we going to think about it? Well, the idea is going to say, look, let's think of it as though there's a little tiny particle. So this is our little particle, and what's going to happen is we're going to think about, where are we? So we're going to think about location at a given time. So now we can think of it as though there's this particle moving through space. And I'm going to put time in quotation marks because it doesn't have to be time, but so this particle moves around. And now you say, well, yeah, I could imagine a particle doing something like this, some sort of strange motion. And with the curve, we say, look, the set of points that get traced out, that will become the curve described by this, we call it a parameterization. So here's our basic idea. This just says what we said a moment ago. But basically, look, we're going to introduce a new parameter that keeps track of where we are at any given point in time. And then as we look over our set of points, lo and behold, then we have a curve. And we call that our parameterized curve. So you can think of it as just there's a curve, or you can think of it as, hey, there's something moving through space, and we're tracing where it is at any given point. Now, it's nice to say, have we seen something like this before? And the answer is yes. Indeed, if we go back to our original way we thought about functions, where we said, well, here's this curve, y equals f of x, and maybe we're going from A, and we want to go out to B. Well, what's the way we can describe it? Well, we say y equals f of x for A less than or equal to x less than or equal to B. But now we say, hey, if we think about it in terms of a parameterization, we can say, now we'll let our x value, we'll just let that be t, and our y value will be f of t. So if you pick any value for t, so here's t, then up here, here's our f of t, and lo and behold, that's our point. So we can think of it as this particle moving along. And there we go. And of course, we're not done, because we really should say, where do we start and stop? And we start and stop for a less than or equal to t less than or equal to b. Now, so that says any curve that we could describe before, we can still describe by parameterization. And not just y equals f of x, we can do x equals f of y. But now we can do all sorts of curves. curves that wind back and forth and do little loopy-loopies. We can do that, and life is good. There's a couple of famous parameterizations that you might be familiar with, and there's one that hopefully you recall from way back in trigonometry days, and that is for the unit circle. And if you remember how the unit circle works, it says, hey, if I have the unit circle, I can describe a point on the unit circle by cosine theta sine of theta. So now our parameterization, our parameter, is an angle, and we get out a point on the unit circle. So as theta varies, we move along the circle, and there we go. Now we should pause and give a one word of warning here. It's actually a great thing, which is to say, if we're thinking about a parameterized curve as just a set of points, then the way to parameterize doesn't have to be unique, which is to say that there's lots of ways to describe the same curve. As a very simple example, so we already talked about how we had this t f of t. So suppose we looked at the following. Suppose we said, let's look at t comma t squared for 0 less than or equal to t less than or equal to 1. Well, it fits this pattern here, so we know what it looks like. It really says, if we think of this as x, this is x squared. And now we're going from 0 to 1, so it says start on the curve x squared at x equals 0 and go to the point x equals 1. So that's the parameterization. In fact, we can be a little bit more precise, because when we have our parameter, there's a natural built-in time. So we're going from 0 to 1. So there's this orientation that comes into play. So we can even talk about how the curve moves along, or rather I should say how the particle moves along the curve. So in some sense what's happening is the particle starts at 0, and we can say it goes over here to 1. Now, what about the following? T squared t to the 4th for 0 less than or equal to t less than or equal to 1. What does that look like? Well, if we think about it, if we say, look, if this is our x, our y is x squared. So it's still going along our x squared curve. We're still going to start at 0. We're still going to end at 1. In other words, it's the same curve. So as a set of points goes, they both are describing the same curve. Now there are differences. For instance, in some sense, if you look at the first case, it says, well, it moves at a constant horizontal speed. In this one, it says, look, t squared. What will tend to happen is it's going to move a little bit slower at the start and pick up towards the end. So it's not quite a constant speed. Now that probably doesn't matter, but that is to say that there are differences. Now you might say, okay, which one is the right one? And the answer is they're both right. It's just a matter of which one do we want to use to make our life good. And the rule of thumb is do whatever makes the computation the easiest. So if you're looking for a parameterization, look for one with a simple expression. The simpler, the better. Because after all, remember, we love ourselves, and we don't want to make our life hard by choosing a parameterization which makes our computations difficult. The simpler the parameterization, the better our computations will be. Now, all right, so we have our ability to make a parameterized curve. What can we do? Not surprising, there's some calculus stuff we can do. So, one thing you can imagine is that we have a parameterized curve. So let's start. We start with our curve, and then we say, okay, our curve is doing something. Who knows? There's our curve. It doesn't have to obey, horizontal line tests, vertical line tests, whatever. And we might say, look, we're interested in what's happening at that point right there. What can we say about that particular point? Well, we do what we always do in calculus, which is we say, well, let's zoom in. So we zoom in a little bit closer, and as we draw it larger, what do we see? Well, what happens is that it becomes a little less curvy. Okay, well that's great, but it's not completely flat, but we're making progress, right? So we say, look, zoom in really close, really close. Okay, and if you zoom in very close, lo and behold, what you end up seeing is it's going to look like a line. And now we say, all right, well, that means we can talk about tangent lines. Because we can say, look, locally our curve is behaving like a flat line. So how do we figure that out? Well, we think to ourselves, how do we find a tangent line? Well, we need a point. That's easy. The point's the easy one. We need a slope. So what can we say? Slope is rise over run. And that just means change in y over change in x. All right, well, that's just what slope is. That's the definition of slope. So how do we find it? Well, what we think of it, say, hey, there's this particle moving. So this particle is going to move a little bit. So if I let time move forward, maybe it moves this way, maybe it moves that way, I don't know, but it's going to move a little bit. So that initially, I'm at this point, which is x of t, y of t, and now if I perturb time, my parameter, by a small amount, that perturbs my location by a small amount. So now we're over here at x of time t plus h and y at time t plus h. So in other words, we've changed a little bit. And now we say, okay, what's the change in y? Well, you take the difference of the y values. Y of t plus h minus y of t. What's the change in x? Okay, take the difference in the x values. All right, that's great. And now we say, hey, we've seen things that look like y of t plus h minus y of t before. It feels like a derivative. To make it feel even more like a derivative, we're going to start with this expression and multiply the top and bottom by 1 over h. Now, if you multiply both the top and the bottom by 1 over h, the net effect is you've multiplied by 1. And that is why you see there's this equality here. It's just a little bit of algebra. So you should really think of it as the top is one piece now, and the bottom is one piece. The h is canceled to get back to the previous step. And we say, hey, that really is looking like a derivative. Technically, it's, a secant line, an average rate of change. But when we think of h as being very small, which of course we're going to think of because that's what happens when you zoom in, h is small, then this looks like y prime. The bottom looks like x prime. And now we're good to go. So if we want our slope, we say, hey, y prime of t over x prime of t. And we're done. So it actually makes a lot of sense. And by the way, you might say, well, what about these approximations? Well, the approximations are because, we're going to get error depending upon how far we zoom in. But if we were to keep zooming in other words, there's a limit involved, our error goes away. So what's the intuition? Well, the intuition says, think about what y prime represents. Y prime says, how is y changing with respect to t? And x prime, how is x changing with respect to t? And so when you put them together, you say, okay, well, if I'm understanding how y prime changes relative to t, and x is changing relative to t, then I can understand how y and x are changing relative to each other by looking at the ratios. Okay, good. So there we go. We can now find our slopes for our tangent lines to parametric curves. Now, a few special notes. One of the things that might happen is zeros. So let's think about the intuition. If y prime is 0 and x prime is not 0, what does that say? Well, it says there's no change in the y direction. So we're not moving up and down, so there's no change in y, but we are moving left and right. So if y prime is 0 and x prime is non-zero, that's our behavior. So that's a horizontal tangent line. In other words, we get back to saying the derivative is 0. Let's suppose we switch though. Suppose we say now x prime is 0 and y prime is not 0. Okay, so what's happening? Well, if x prime is 0, that says there's no left-right motion. So that says we're just staying put in the x direction, but y is changing. So we are going up and down. So now our line is behaving like this. It's something going straight up and down. That means we have a vertical tangent line. Now, what if they're both 0? Well, then we have a 0 over 0, and we know what that means. More work. More work. So if they're both 0, well, we think about what's happening nearby and see what's happening as we look closer and closer. What if you wanted to do the second derivative? Now, if you think about the first derivative, you say, hey, first derivative is super easy because first derivative, you just say derivative of y over derivative of x, and we're done. So you might think, well, second derivative, isn't that just take two derivatives of y over two derivatives of x? No, that wouldn't work. In fact, you can convince yourself it wouldn't work pretty easily. See, suppose you had t comma f of t. So we were back into our old setting where we had y equals f of x. If we were to take two derivatives of the y part, that would be f double prime of t, which is great, but two derivatives of the x part would be 0, and that equals something which is silly. Doesn't work. So it's not just a matter of taking two derivatives over two derivatives. Okay, all right. So what is it? Well, let's dig into it. What does it mean to talk about the second derivative? Well, it's the derivative of the derivative. Okay, that makes sense. No surprise there. And when we talk about derivatives, we're talking about how things change. So if I want to know the derivative of dy dx, well, I'm saying, how am I changing dy dx relative to how am I changing x? So I'm looking at that ratio there. Say, okay, all right. Well, how can we talk about change in x? That says take a look at the derivative of x. That's how x is changing. If I want to know how the dy dx is changing, well, okay, I know what the expression is. We found it. It's y prime over x prime. So we take the derivative of that. And now we do a little bit of work. See, in the numerator, what do you have? Well, you get a quotient rule. So you take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom term squared. Now that's just the derivative of the top. Divide that by derivative of the bottom, x prime. And you can see we can move this x prime up, put it with this other x prime. So we get this interesting looking expression. X prime of t, y double prime of t, minus y prime of t, x double prime of t, all over x prime cubed. Okay, wow, okay. Maybe not what we expected. Is it at least consistent? What if we had this as our x of t and y of t? So what would happen? Well, we'd have x prime is 1. Y double prime would be f double prime. Okay, minus f prime, not looking good there, x double prime, aha! That would be 0. And then divided by the derivative would be 1 cubed. And lo and behold, it gives us exactly what we want. So that says at least it's consistent when we think of our y equals f of x setting. But of course, it's more than just consistent there. It works all the time. So that's the basic ideas. Okay, so now we have our ability. We can talk about parameterized curves. And it's going to be a fun topic. And we're going to talk more next time about applications. But for now, I think it's useful to say, well, let's practice taking tangent lines. Let's practice drawing them. Let's practice recognizing them. And become a little bit more comfortable with our notion of parameterized curves, which means time to go do some practice. See you soon.